Okay, let's dive right into this. We're all surrounded by AI that makes some pretty big decisions, right? Everything from what you see online to, even medical diagnoses. But how do we know we can actually trust these super complex models to get it right? Well, that is exactly what we're breaking down today.
So, look, you've built a model. It seems to work great on your data. That's awesome. But that's just step one. The real challenge, and this is what separates a cool little experiment from a tool that's actually reliable, is proving it's going to perform accurately out there in the real world on data it has never, ever seen before.
So how do you test a model? Well, the most straightforward approach, it seems pretty simple, pretty logical. But as we're about to see, it has this one fundamental weakness that can lead you completely, totally astray. This is what we call holdout validation. You just take all of your data and you slice it into two pieces. You've got a big training set for the model to learn from and a smaller testing set to grade it. Simple enough, right? The model basically studies for the exam with the training data, and then it takes the final test on the testing data. But here is the massive catch. What if, just by pure random luck, you got a really easy test set? Or what if you got an unusually hard one? Your performance score could be, misleadingly high or just disappointingly low. Relying on just one split is kind of like judging a student's entire intelligence based on a single pop quiz. It's just not that reliable. So, to solve this problem, this issue of a single potentially biased test, we need a much more robust system, a smarter way to evaluate our models. And that system is called cross-validation. The core idea here is really simple. It's all about repetition and rotation. Instead of giving your model just one test, you're going to give it multiple, different tests. And by doing this, every single piece of data gets a chance to be used for both training and testing. And that gives you a much more stable and, frankly, a much more trustworthy measure of your model's actual quality. And this is absolutely crucial in practice. Cross-validation gives us a realistic estimate of how the model's really going to do. It lets us fairly compare different models head-to-head. It helps us fine-tune their settings without cheating. And it just makes sure we get the most value from every single data point we have. So how does this actually work? Let's get into the playbook and look at the most common, the most important technique that pretty much all professionals use every single day. So, meet K-Fold cross-validation. You can think of this as the industry standard, the go-to method. It's the one you're going to see most often because it strikes this fantastic balance between being really reliable and not taking forever to run. Okay, so what you're seeing here really visualizes the process perfectly. First, you split your data into a number of equal chunks. We call them folds, let's say 5. Then you hold out that first fold just for testing, and you train your model on the other 4. You get a score, you write it down. Then you rotate. You use the second fold for testing and train on all the others. You do this 5 times until every single fold has been the test set exactly once. Then you just average those 5 scores together for one final, super reliable performance metric. But K-fold has a smarter cousin, and it's designed for a really common type of problem, classification. See, while standard K-fold splits the data randomly, stratified K-fold is a bit more clever. It makes sure that the proportion of each class, like say fraud versus not fraud, is the exact same in every single fold as it is in your overall data set. And this shows you exactly why that matters so much. I mean, imagine you're building a model to detect a rare disease. If one of your test folds randomly ends up with 0 examples of that disease, your model's going to get a perfect score for that round, but it's a completely meaningless result, right? For things like medical diagnosis or fraud detection or really any problem with imbalanced classes, stratified K-fold isn't just a nice to have. It's absolutely essential. Okay, so K-fold and stratified K-folds are your workhorses. They're what you'll use most of the time. But what about more specialized situations? Let's do a quick lightning round of a few other powerful tools that you should have in your toolkit. First up is leave one out. This is the most extreme, most thorough version of K-fold you can imagine.
If you have 100 data points, you train on 99 of them and test on just one. Then you repeat that 100 times. It's incredibly thorough, but all that repetition makes it painfully slow. It's really only practical for very, very small data sets.
Next up, time series cross-validation. Okay, so standard methods assume your data is all independent, but that's just not true for things like stock prices or weather data. The order matters. This method respects that time order, always training on data from the past to predict data in the future. It stops the model from cheating by looking ahead in time.
And finally, there's nested cross-validation. You can think of this as the gold standard for serious academic research. It basically has two layers, a loop inside a loop. The inner loop finds the absolute best settings for your model, and the outer loop tests how well that perfectly tuned model performs. It's a really rigorous process that gives you the most honest and unbiased performance estimate possible.
Okay, so with all these options, how in the world do you choose the right one? Well, it's not about finding the single best method. It's about finding the best one for your specific project. So the key takeaway here is that your choice really depends on the context. Is it a classification problem with imbalanced data? You have to use Stratified K-Fold, no question. Is it a forecasting task? Well, time series CV is the only way to go. Is your dataset absolutely enormous? A simple holdout split might actually be good enough. This table gives you a really clear way to make that decision.
But even with the perfect technique, it is so easy to make mistakes that can just totally invalidate your results. The absolute biggest one is called data leakage. This is when information from your test set accidentally contaminates your training process. It's like giving your model the answers to the test beforehand. Doing any data preparation before you spill the data is another common way this happens. These mistakes can make you think your model is a genius, when in reality, it won't work at all on new data.
So let's bring it all home. We've been talking a lot about the what and the how, but let's just focus for a second on the why. Why does this technical process matter so much?
Because at the end of the day, we need to build AI systems that we can actually trust. Cross-validation is the bedrock of that trust. It's the process that ensures our models aren't just getting lucky on one particular test, but that they are genuinely robust, they're reliable, and they are ready for the messy complexities of the real world.
I mean, think about it. From the loans we're offered to the medical advice we might receive, models are making decisions that have a real impact on our lives. This isn't just about getting a high score on a leaderboard. It's about building a future with AI that is fair, that is reliable, and that's worthy of our confidence. And all of that starts with rigorous, honest validation.